Hopefully you came up with a pattern for the antiderivative of a function of the form x to the p. Turns out that the antiderivative of such a function, capital F of x, would be x to the p plus 1 over p plus 1. So think about when you did power rule. What did you do procedurally speaking? You would take the exponent, move it to the front, and then subtract 1 from the exponent. You would take the exponent, move it to the front, and then subtract 1 from the exponent. So think about what that procedure would be in reverse. Multiplying by the exponent and then subtracting 1 from the exponent. Doing the reverse of that in the reverse order would be exactly what we have here. First add 1 to the exponent and then divide by that new exponent. We're going to use this idea to find the antiderivative of some more power functions. It's always important to remember the plus c when you're taking antiderivatives. So let's apply this procedure to find the antiderivative of these functions here. First example, we have f of x equals x to the negative third power. So capital F of x, the antiderivative would be add 1 to the exponent and divide by that new exponent, which means what we would have is x to the negative second power over negative 2. So if you want, you could simplify this a lot of different ways, but one way is to say that it's negative 1/2 x to the negative second power. What about f of x equals square root of x? Well, before we take any antiderivative, it would be helpful if we write it in the form x to the p, which would be x to the 1/2. Let's calculate the antiderivative. Capital F of x would then be x to the 1/2 plus 1 all over 1/2 plus 1. What's 1/2 plus 1? Well, it's 3/2, which means we end up with 2/3 x to the 3/2. And we don't want to forget the plus c. Unless we're told otherwise, we want to always give the most general antiderivative. So if you see an instruction that specifically says the most general antiderivative, then you should definitely remember the plus c. Let's take a look at some trig functions now. So let's say there's some function where you take the derivative and you end up with sine x. Well, we know that when we take the derivative of cosine x, we're going to end up with negative sine x. We're in another situation where our guess is pretty close, it's just off by a constant multiple. In this case, the constant is negative 1. That means that a better answer for the antiderivative of sine x would be capital F of x equals negative cosine x plus c. Again, practice checking the antiderivative guess by taking the derivative of this answer and checking that it ends up where it should be. It should end up simplifying to exactly sine of x. Similarly, with f of x equals cosine x, little f of x equals cosine x, we would make a guess that the antiderivative would be sine x, because we know that the derivative of sine somehow involves cosine. in this case, we actually end up with exactly the right answer, which means we can just say that capital F of x in this case is just going to be sine x plus c. Here's a table that summarizes some of the anti-differentiation formulas we've been talking about and gives you a few more. So if you have a function times a constant, the antiderivative, forgetting the plus c for a moment, would be c times that antiderivative. If I have two functions added together and I take their antiderivative, then we add those antiderivatives together. If I have a function of the form x to the n, a power function, where n is not equal to -1, you'll deal with this case in Calc 2, then I apply what I would call the antiderivative power rule, where you add 1 to the exponent and you divide by the new exponent based on that pattern we observed in a previous slide. Cosine x, an antiderivative of it will be sine x, as we observed. The antiderivative of sine x would be negative cosine x, because the derivative of negative cosine x would be negative sine x, which gives us back the sine x. Secant squared x we should recognize as the derivative of one of the trig functions. So the antiderivative of secant squared x is tangent of x. And secant x tan x we should also recognize as the derivative of some function. Turns out that that function is secant x. Now you might be wondering, why don't we talk about the antiderivative of secant x? Well, that will come in Calc 2, strangely enough.